Blah, that voice. Okay, hey everyone, thanks, and thanks for coming to this week's Deep Learning Theory Series seminar or AI Theory seminar, depending on what what I say. Okay, so the speaker today is Yahong Yang. So Yahong is at Georgia Tech, and his specialty is, well, pretty broad, but say deep learning theory. So from all aspects. And today, actually, I came across one of his papers. Well, there's many of his papers, but here's the one, it's related to the one I asked. So this is about deep neural networks with general activation functions, super-convergence on Sobolev norms. So it's quite an interesting area of research, I have to say. So after you.
Okay, okay, so that's for the invitation and the introduction. Okay, so today I want to talk about some, maybe I will mostly focus on the approximation theory and the generation analysis for the deep neural network in solving the partial differential equation. So this is what I'm going to talk today. So today I will first quickly give you some background about neural network in solving the partial differential equation. Then I will go through what is approximation error in neural network solving the partial differential equation. So I will just going to discuss what is approximation result for deep neural network in the Sobolev space. So my first result will show that for the deep neural network, maybe we can achieve the better approximation rate compare with traditional method. So this maybe give us a motivation for us to use neural network in solving the partial differential equation. But the first result, I will need to know that, of course, there is some benefits for deep neural network. But if we still consider in the Sobolev space, this approximation result will still have the cursor of dimensionality. So maybe later, so in the second part, I will going to discuss how to overcome the curse of dimensionality for deep neural network. And in the later, I will just mention a little bit about proof of optimal of the approximation rates. And then the last part, I will just go to a little bit about the generation error. In this part, I want to just discuss something very interesting topic. So we know that a deep neural network have some two. Maybe you can consider have two kind of structure. One is very deep neural network. Another is a shallow neural network. So when we should use deep neural network to solving the problem, when we should use a shallow neural network to solving the problem. So you can see the title here. I will discuss the deeper neural network or wider neural network. In which problem we should use a deeper, which problem we should use wider. So this is what I'm going to talk about today. And before that, let's quickly go through some definition about deep neural network. I just assume that a lot of you already know this definition, so I go through this part very quickly. So today we just consider about a very simple, maybe just very basic neural network structure. We just call it deep neural network, which is fully connected. So in this kind of neural network, there are only two kind of components. One is a affine mapping. Here, this is a affine mapping, a linear affine mapping. Another is a nonlinear compositions. So in the mathematics, we always use two terms to describe the complexity of the deep neural network. The first will become, we use the dips. This dips, what it means dips? Dips, it means that the max size of the Wi in the affine mapping. And the second term is dips. Dips, which means that the number of nonlinear compositions. So for example, here, this is a very simple deep neural network structure, and this neural network structure with is depth 2 and width is 4, because that we do 2 times nonlinear compositions, and the max size of the matrix will become 4 times 4, so width will become 4. Okay, so now today I was this at if you want to use neural network to approximate some target function or solving the partial differential equation, there are three kind of error in the error analysis. The first kind of error we call it approximation error. This kind of error is going to describe how well the neural network close to your target function or target solution of partial differential equation. This is that we just establish a neural network with some unknown parameters, and then there exists what's the best parameter to approximate this target function. And the second kind of error, some places called the estimation error, and some places called generation error, some places called estimation error plus approximation error, plus them together, which is called generation error. Both are okay. So here I just call it generation error. Maybe when you read some paper call this part as the estimation error. This error is raised from that we only have the finite data. So which means that here we because that we don't if we have infinite data, we are able to find this best approximation for the best approximation neural network to approximate the target function. But in a lot of cases, we only have finite data. So generation error are going to describe the gap between the best neural network and the neural network we can learn from the finite data. This part we call it generation error. And the last part of error is called the training error. Training error means that, okay, even if I just use finite data to learn that loss function, but I still cannot learn the global minimum for that loss function. This is because that sometimes, raise your head.
Oh yeah, yeah.
Oh.
Yeah, but maybe after you finish this, I have a question. Like a
Okay, okay, good, good, good. Okay, so the training error, which means that okay, we only just catch learn some local minimal for the loss function, not global minimal. Okay, I recently I spend a lot of times on the training error, but here due to the time limit, so in this talk I will mostly focus on the approximation error and the generation error. Okay.
cool. Yeah,
Mhm.
actually, maybe one small
Sure.
question. So
Mm,
when you say generalization error, do you
mm.
mean like the fact that maybe you want to sample the function only at finally many points, or do you mean the fact that the samples could be at random locations and have noise?
If your data have some noise, which means that I combine both with my generation error. If your data is not have some noise or something like that, maybe only the first part will become your generation error.
Okay,
Yeah.
okay, cool. That's I
Mm.
thought. That's something to clarify. Cool.
Okay. Yeah. 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 Okay. So first of all, let's go through the approximation error for neural network solving the partial differential equation. In this part, I will just I want to answer the two questions. Can deep neural network approximate the solution of partial differential equation? And then the second question is that why we use neural network to solving the partial differential equation? What is the advantage for neural network in solving the partial differential equation? So first of all, I think that a lot of you are already or have already read a lot of paper about neural network solving the partial differential equation. So here I just give you some maybe two or one basic method for solving the partial differential equation. The first method is very famous called physics informed neural network, and this is and this neural network just this method just use the residual of the partial differential equation to become our loss function to solving the partial differential equation. For example, if I want to use a physics informed neural network to solving such partial differential equation, okay, the continual formula loss function can be read as in this kind of formula. And you can just regard that if I replace U by neural network, this will become continual formula of loss function. And in the mathematics, we can prove that this loss function is equivalent to the H2 error between U and U star. Here, U star is the exact solution of this partial differential equation. So which means that if you want your neural network are able to solving this partial differential equation, you should make sure that there is a neural network which makes that this neural network minus the gap between this neural network and the exact solution, the under the H2 norm should become very small. And similarly, you can just consider other kind of method like deep race. Deep race will use the variational form to become our loss function. And we can still use some new mathematical way to prove that the continual formula loss function is equivalent to the H1 norm. So which means that if you want to make the deep race method work for neural network, you still need to make sure that there is a neural network can make sure that you can approximate the target function is the error should become small under the measure for the H1. And of course, there are a lot of methods. So this is the main difference from the neural network solving the partial differential equation and the neural network to approximate the target function. If you just want the neural network to approximate the target function, you just need the neural network have a small gap with the function, with the target function itself. But if you want to use neural network to solving the partial differential equation, you are not only require neural network to approximate the function itself, but also require the derivative of neural network to approximate the derivative of function itself very well. Even sometimes we will require higher order derivative. So this will become our first question is that can we use the neural network to approximate the function in Sobolev space and measured by Sobolev norm WNP? Okay, this is become first question. As so here I just share some very to give you some background of this kind of problem. So for the traditional method, for the traditional method, if you just want to use a finite element, finite difference, or some other other kind of traditional method to solving this kind of problem, the optimal rates for the traditional method will become m power of n minus m over d. Here, m will become your freedom of your approximator. For example, if you want to use a finite element to approximate your target function, this m will become your number of bases. If you want to use the neural network to approximate the target function, this m will become number of the parameters. Okay, so here this m will become number of parameters. D will become the domain for the input function, for domain for the sorry, domain for the target function. And here, the n will become the regularity for your target function. M become your regularity for your norm to measure the error. So this is a traditional method. And Devol in very earlier have already proved that if you just consider a continual approximator like finite element, finite difference, okay, this will become optimal rate. And recently, people are already consider about a lot of work about use shadow neural network to achieve such kind of test. At the optimal rate for the shadow neural network, you can find that it still become the same approximation rate compared with the traditional method. Okay, so this is in some paper we have already in I think in the second paper we discussed this a lot, and also this kind of there are a lot of relative work. I think that the people in the people have already started this maybe 10 or 20 years. So there are a lot of very good work based on the shadow neural network, like a barren space, something like that. Okay, all is based on this part. And here I just want to mention that, okay, so you can find that if I just use shadow neural network to solve this kind of problem, maybe in the in the approximation rate, we cannot find some advantages. But here, if I use the deep neural network to achieve this kind of approximation, you can find that we are able to obtain the better approximation rates. And this rate, we always call it the super convergence rates, which means super convergence, which means that if the approximation rate is better than the optimal continual approximator, so this kind of approximator we call it achieve the super convergence rates. Here we can find that compared with the traditional method at the shadow neural network, here we have more two at here. But here, when we will require deep neural network where L is very large. Here, L describes the depth of neural network. We are required this part is large. And in the detail proof, we just prove that, okay, the approximation rates, if we use N and L to describe the approximation rate, this will become our approximation rates. Okay, so you can find that, okay, if we use deep neural network, we will have some benefits. The reason, later maybe I will show a little bit about the proof, but the reason is if you just want to understand why it is work, you can just consider about that. If I just use shallow neural network or traditional method like finite elements to achieve approximation, then if when I add the number of parameter, we just add some basis. You can just regard we add some basis. So to achieve a better approximation rate. But for the deep neural network, if we add a number of parameters, If we just fix the depth at fix the width and increase the depth for a neural network, which means that if I increase the number of parameters, I increase the number of nonlinear compositions. And if you do the nonlinear compositions, which will make your function have more complex structure. If the function have very complex structure, which means that this function has better ability has better approximation ability. So this is some you can regard this is one of understanding why deep neural network can achieve approximation rate or can achieve better approximation rate compared with shallow neural network. And of course, here later I will just show a little bit that okay, this approximation rate is nearly optimal if you consider activation function is ReLU or ReLU power of k. Okay, if you just regard it as if you activation function is ReLU power of k, this kind of rate is nearly optimal. But if you consider some very general activation function like some tanh, like some GLU, like something like that. Okay, that will become that part I can still obtain such approximation rates, but I cannot prove that that rate is optimal. This will still become open problem. Okay, so let's go through. Okay, so here I just want to make sure make some comments that okay here our rates can be used for nearly all the famous activation function. So which means that in this kind of paper we prove that nearly all the famous activation function, the deep neural network can achieve the nearly can achieve super convergence. Of course, there are some kind of work have already studied about super convergence, but they just consider about ReLU or square of ReLU or something like that. But in our paper, we just general to nearly all the activation function, like here tanh, arctangent, and GLU, something sigmoidal. Okay, all of this kind of activation function, you can achieve the super convergence. Okay, so let's quickly go through a little bit about proof, but I will not go through too many detail. Maybe some of you are interested in why it can achieve the super convergence. I will show a little bit about some insight. So the way to achieve the proof is not very difficult. The way to achieve a proof, the first step is that we first consider approximate the target function locally. So how to approximate some function locally? We want to use a polynomial to approximate some target function locally. And this is very easy to achieve because that will, if the function is become smooth function, you can use a Taylor expectation to achieve this kind of approximation. But if the function is belong to the Sobolev space, okay, maybe we will not have Taylor expectation for the Sobolev space, but we can still use average polynomial. This is some technique in the numerical analysis, which means that we can still use the polynomial to achieve a local approximation for the target function measured by the Sobolev norm. Okay, and then we just combine all of local approximation together. So which means that we are nearly to achieve the approximation by the following form. Here the xk is just keep it as same, but here the pk will become the piecewise constant function. Okay, so here we just use a local approximation and combine them together. And then we find that this kind of formula are able to approximate our target function. So later, we just consider that use neural network to approximate such kind of function. And then we find that, okay, so if we want to use neural network to approximate such formula, we need to approximate three kind of things. One is x power of k, and another is a multiplication, and secondly is about pk. So the first two parts, xk and multiplication, this kind of approximation you can just use Yaros, use a lot of traditional numeric. There are a lot of results for neural network approximation to approximate the multiplication at the x power of k. I think Yaroski did a lot of work related to this part. So this part is very, very simple. You can use a log complexity neural network to approximate this two part very, very well. So the difficult part is that we want to use a neural network to approximate PK. PK will become piecewise constant function. So here we just use some bit neural network technique to approximate this part. And this work is have already been established in a very earlier, not very earlier, 6 years before, just 6 years, but they just publish, they just post this paper online in 2017, so maybe 8 years, 8 years before. Okay, in that kind of what is bit neural network? Bit neural network is kind of work can be used to approximate using ReLU neural network to approximate some piecewise linear function, and the bit neural network shows that we can use deep ReLU neural network to approximate the piecewise linear function very efficiently and well without some small range. So this is some reason why we can achieve the super-convergence, because that the deep ReLU neural network are able to approximate the piecewise linear function very well. The detail you how to achieve this, you can achieve this part, but this part is very makes sense because ReLU will become piecewise linear function, and if you want using piecewise linear function deep piecewise linear neural network to approximate the piecewise constant function. Of course, sometimes we can find some trick to make this approximation is very efficiently. So here, my question is that, okay, this kind of way can only approximate the target function without some small kind of range. This small kind of range, of course, right now, we still cannot approximate it very well, as this small kind of range is very important because that the derivative in this part is will become very large. So we need to just consider about how to control this part. So in the third step is that, of course, we have in the first two step, we have already showed that we can establish a neural network to approximate the target function very well, achieve super convergence without in the small range. Now we need to consider how to remove such kind of small range. The idea is that we should introduce some partition of units and to make that band range is located as a support is located outside the support set for the partition of unit, then combine them together. This will become our so this kind of neural network, you can just find that it is established by ReLU at the ReLU power of n+1. Here, ReLU power of n+1 is going to approximate a polynomial at the multiplication. Okay, and then we can for this step, after this step, we can establish a neural network with activation function ReLU at the ReLU power of n+1 to approximate the target function in the whole space, whole domain, as measured by the Wm infinity norm. Okay, but so for the last step is that we don't want to use the ReLU at the ReLU power of +1 to become our activation function. We want to use very general activation function to achieve such kind of approximation rate. So the last step is that we want to substitute the ReLU at the ReLU power of n+1 to some very general neural network, to some very general activation function neural network. So then in our paper we prove that if the activation function satisfies some condition, then we can use the fixed width at a fixed depth some sigma at a neural network to approximate the ReLU at the ReLU n+1 very well. So this can give us a chance to replace ReLU at the ReLU n+1 to to some very general neural network. And what is this condition? This condition is very simple and very easy to achieve. We just require this sigma, this activation function is satisfied local smoothness, which means that you can find some small kind of range. In this kind of range, the function is very smooth. It's infinite smooth. The second part is that, okay, the activation function should satisfy some decay rates for its derivatives. Okay, so it's descent. So this is our second kind of sense. And this kind of activation, this kind of property is very easy to achieve, like arctangent, GLU, something, a lot of neural network is very easy to achieve this kind of things because you can think about the tanh when you do the derivative, okay, it will become something like a Gauss distribution. And when you do the lot of how many times derivative, the decay speed will become faster and faster. So a lot of activation function will satisfy such kind of property. So we prove that if you have satisfied such kind of two property, you are able to replace ReLU at the ReLU power of n+1 to such kind of general activation function. Then combine all the steps together, we can achieve the super convergence for the neural network with the general activation function with on in the Sobolev space measured by the Sobolev law. Okay, so this is just a quickly go through the definition, go through the result and go through how to prove it. But you can just think we can also see the result. This result, of course, is nice because that is better than the traditional method. Okay, it's better than the traditional method, but it will still have the cursor dimensionality. Maybe some of you have go to listen a lot of seminar, and a lot of people have already told you that okay, the neural network is very good. It can solving the curse of dimensionality. But here, our result here is still have the curse of dimensionality. What is the curse of dimensionality? The definition of the curse of dimensionality is that if I fix the error, okay, and going to increase the dimension of the input. If I want to fix the error, the number of the parameter required should grow exponentially depends on the dimensional. So of course, this result will still have the curse of dimensionality. So this is result is so this result based on this result, we just consider about can we improve this kind of results? The re, the so After we check about this kind of approximation rates, the answer is not very good because that we prove that this kind of approximation rate is nearly optimal in some kind of activation function like the ReLU at the ReLU power of k, something like that. It is nearly optimal. So we cannot improve about this kind of things. And the reason why this we cannot improve it because that we consider the approximation in the Sobolev space. The Sobolev space is too general. There must contain some very high, truly high dimensional structure function in the Sobolev space. And if this function is truly have very high dimensional structure, we are not able to approximate it by the low dimensional structure with very good approximation rate. They are impossible. So based on this motivation, you can just consider about how to solving the curse of dimensionality. Oh, sorry, here is a typo. Here should become n minus m. Okay, so there is a so which need to consider about how to solving the curse of dimensionality. If we want to solving the curse of dimensionality, we cannot consider about the approximation in the Sobolev space. We need to consider about some approximation in the subspace for the Sobolev space, like Barron space, like Kolmogorov space, like some lot of space like Radon-TV non space, not Radon-TV space, something like that. Here there are a lot of work, so I didn't, I did, I does not, I do not list a lot of at here. So I just mention a little bit about Barron space and Kolmogorov space. Barron space is kind of way are very easy to achieve the some neural network approximation to without a curse of dimensionality. But in my opinion, most of theoretical result for Barron space is going to establish a neural network is going to establish under the shadow neural network. Okay, based on the shadow neural network. So if we want to establish some approximation rates for the deep neural network, Barron space for that part is still become some open problem. Okay, so in this talk, because I want to share some result for the deep neural network, so we will not discuss a lot of things about the Barron space. So let's go into describe something about the Korobov space. And Korobov space is also the subspace for the Sobolev space. And the Korobov space is something that is widely studied in the numerical analysis and also widely studied in the physics, as there are some work have already studied about it. So what is the Korobov space? Here I just want to show the definition. This is the definition of Korobov space. The definition of correlable. Oh, sorry, here is a typo. Here should become n should become two. Sorry about that. This should become two. This should become two. Okay, so the definition of the correlable space is very, very similar with the Sobolev space. And the only difference between the definition of the correlable space and the Sobolev space is that here the norm of index in the Sobolev space, the norm of index here should become norm of one. But here, the Kolmogorov space, the definition of Kolmogorov space here, this one will become infinite. So this will become the only difference between the Korobov space and the Sobolev space. And based on this definition, you can know that, okay, if this kind of function should still exist, it should still exist as it belongs to the LP. So this is main difference between the Korobov space and the Sobolev space. So we are not only that each direction we can do two times derivative, but also we can combine them together. So this will become something very different from Sobolev space. Sobolev space means that okay, if the regularity for the Sobolev space is two, the total number for the derivative we can only do two times. But for the Kolmogorov space, of course, the regularity something still become two, but this just tells us that we can do the two times derivative in the each direction and combine them together. So this is the difference between Korobov space and the Sobolev space. And this space is very widely studied in the physics and in the chem and also in the chemistry and also in the mathematical numerical analysis. The reason is that I think that because that this solution has some physical meaning because this solution can be proved it is belong the solution or sorry this space is have a lot of physical meaning because that the solution of electricity shielding equation we can prove that the solution of it is belongs to the Korobov space and there are some work have already proved some regularity of Korobov space. This is but for this is something that's different from barren space. Barren space, recently, a lot of people are trying to prove that some regularity result from the barren space because we want to give some physics meaning or some application for the barren space. So we should prove that which in which kind of PDE the solution is belongs to a barren space, something like that. But for the Korobov space, you don't need to prove that. There already have some results. So this is very good for the Korobov space, very good for its application. And so let's go through the some results for our recently established the deep neural network approximation for the Korobov space. So first of all, we just consider about traditional method. I have already mentioned that there are a lot of traditional way to solve Korobov space have already been studied very well in the traditional method. So like Professor Jason and Professor Chandu have some paper related to this part. And we know that for this part, so the traditional method, the rate will become the m power of minus 1. And here we have some log term. Log term will still have the cursor dimensionality. But if you do not consider about log term, just consider about the polynomial term, okay, this result is very good. It can overcome the cursor of dimensionality. And recently, we just generate this to deep neural network, and we can find that, okay, we can achieve the better approximation rate for even for the Korobov space. Here, the rate can be the better. Okay, and then later recently we just consider about because that this recently we consider about this log term. Sometimes it will still become a problem, become an issue because that when m is large, when d is large, this term will still become very large. This is still not very good term. So right now we want to just remove this log term, but we find that to remove this log term will become very hard. If we remove this log term, okay, the in front of coefficient will also become exponential will exponentially depends on the d. So we which means that that result maybe if we didn't add some assumption or structure into our approximation, the result will not become very clean. So right now in our recently work, we just establish the deep neural network to approximate the symmetry Korobov space. And if we just consider approximate some symmetry Kolmogorov space, Okay, this long term, we can just totally remove about it. But here we can only achieve the some approximation rate, which is the same, little bit same with the traditional method. How to combine the last two results together? This is still become open problem. We still cannot solve it right now, and didn't have an idea about that. Okay, so this will become some result in Korobov space. So in the Korobov space, you can find that okay, there is no no curse of dimensionality, especially for the last result. Okay, this result is totally without the curse of dimensionality. So this just tells us that if you want to neural network to solving the curse of dimensionality, okay, then you should consider some space which is should become subspace of Sobolev space. And then this also shows that why the neural network sometimes we do the experiments, it can overcome the curse of dimensionality. The reason is that of course, maybe that solution is located in the very high dimensional space, but that solution or that targeted function has some low dimensional structure. For example, it belongs to a Kolmogorov space or is just located in some low dimensional manifold or something like that. Then when you use neural network to approximate it, the neural network can quickly catch that dominant part. So then the final result, something like that, the neural network can overcome the curse of dimensionality. So this just tells us there is no magic behind the curse of dimensionality. If you want to overcome the curse of dimensionality, you must have that your target function has some low dimensional structure. For example, I just gave you one kind of experiment example. For example, we are consider going to solving this very simple partial differential equation, but we can let this d become large. Here we can let this d become 100. Okay, let this d become 100. So which means that this partial differential equation is located in the very high dimensional space. Okay, so this is located in a very high dimensional space, but if we just let fx become some special term, then we can find that this ux it's just look like this way. This is just exactly solution of this partial differential equation. And of course, this kind of function is belongs to the Korobov space because you can do the two times derivative for each direction and combine them together. And of course, this kind of function is satisfy the symmetry structure is have a symmetry structure. So based on this kind of partial differential equation, we don't need too many neural to approximate it. Here we just use the dips is 3, n is 2 that we can achieve very good approximation. Here we can just find that we just use very small neural network size, but even for d is equal to the 100. In this paper, we consider how to do the sampling, but here due to time limits, I cannot go through detail how to do the sampling. But after I just use our sampling way to do it, you can find that even for d is equal to 100, the approximation rate can still become acceptable. This is a good approximation rate. The good equity in the neural network. Of course, it's not good in the traditional numerical analysis, but it is already very good in the neural network. So the reason why we can achieve this, the mathematics behind it is that okay, of course, this partial differential equation has a very high dimensional structure, but its structure is very simple. Or not located in a very high dimensional space, but its structure has some low dimensional structure. So we can use neural network to achieve the approximation, and it same can overcome the curse of dimensionality. Okay, so this is just two kind of approximation result. That the first result is very general, but has a cursor dimensionality. And the second result is considered in very special space, but is without cursor dimensionality. And of course, here I can also show that our proof is nearly optimal. But the way to prove optimal, prove optimal is that we consider about to bounded the VC dimensional for the neural network space. So what is VC dimensional? This is the definition of VC dimensional, but you don't need to go through the detail if you're not familiar with it. You just need to understand this is just a number. Basic dimension is a number to describe the complexity or richness for the space. Okay, so which means that if the basic dimension is very large, then which means that this space is very complicated and very richness in the approximation. It have very large high is the approximation ability is very good. So right now, what we want to do is that if we want to prove the optimal of the approximation rate for the neural network, we need to give the upper bound for the basic dimensional for the neural network. Okay, but this kind of things is already done by a lot of people. But our new thing is that because that we want to consider about optimal approximation rate for the neural network in the Sobolev space measured by the Sobolev norm. So the difference is that we should not only consider about basic dimensional for the neural network itself, but we still need to consider about the derivative for the basic dimensional. And even if you consider about the measure by the very high order Sobolev norm, then this part you should consider about higher order derivative for the Sobolev norm. So for the neural net for the higher order derivative for neural networks under the basic dimensional of this kind of space. Okay, and the this is our results, and the way to obtain it is a little bit complicated. You need to know how to divide the space, and then to calculate each basic dimensional in subspace, and then to solve it. So due to time limit, I just escape this part. If you are interested, I can share you some paper, and we can discuss about maybe some later. Okay. So this is about something about the approximation results, and I will go through very quickly about the generation error. So right now, I have just tell you that for the deep neural network, if you want to use deep neural network to solving the partial differential equation or approximate some target function, it will be better than the traditional method, better than the shallow neural network. But why it is better? This is because that with the same number of parameters, deep neural network can establish more complexity structure for the for the neural network. So this kind of complicated structure can have a better approximation ability. But this is not. But you can think about because that the structure is more complicated. Then, if you want to learn this kind of structure, you should use more data to learn such kind of structure to catch more complicated feature. So this will become so this just tell you the one story is that you can just I didn't give you the experiment result, but you can think about this is very natural. So which means that deep neural network, when deep is increased, okay, when we have a very deep neural network, the approximation rate will also increase, but the generation rate will decrease because the function will become more complicated. We need to use more data to catch that part. There will become very natural question. In which cases we should use deep neural network, and in which cases we should use very shallow neural network to solve this problem. So in order to answer this question, we give the nearly optimal rate for the deep neural network and the shallow neural network. And for the shallow neural network, the generation error have already been given. Okay, because that for the shallow neural network, people are ready to study about the carving number, basic dimensional for the shallow neural network. And because the most important step for me in shallow neural network is that when we establish the approximation for the target function by the shallow neural network, we can assume that the parameters in the neural network has some uniform bounding, which means that the parameters in the shallow neural network to achieve optimal approximation, all the parameter in the neural network has some uniform bounded. But for the deep neural network, this will become impossible because that you have already see the proof. In the proof, we use the ReLU to approximate the piecewise constant function. And if you want to use the ReLU to approximate the piecewise function very well, there must have some jump. Because this jump, will require the parameter become very large. So this large, so we cannot, so which means that assumption in the shallow neural network is not work in the deep neural network. So for the deep neural network, this is the most important things. This is the most important things. We cannot use the way to bound the shallow neural network to bound the generation error of the deep neural network because we didn't have the uniform bound for the neural network parameters. And the way to do it is that our contribution right now is that we also find a way to obtain the optimal generation error rate for the deep neural network without uniform bounded assumption. The way to do it is that based on this kind of way, we bounded the generation error by random complexity, and bounded the random complexity by Kelvin number, and bound the Kelvin number by the basic dimension of derivative or higher derivative for the deep neural network, and bounded the basic dimensional of derivative of higher derivative of neural network. We don't require that the parameters is bounded. We just require the output is bounded and the number of parameters is bounded. A number of parameters is bounded is well known. This is what we need. Then we can just bound it basic dimensional. So based on these results, we can achieve the optimal generation error for very deep neural network. Here, W will become number of parameters. M will become the number of sampling points, and N will become the regularity of target function. K will become the regularity of your loss function, which means you can just think about it is the regularity of the Sobolev norm for measure the error. Okay, K will become regularity of the loss function. So this will become the generation error for deep neural network, and this is generation error for shallow neural network. You can find that for deep neural network, approximation is better than shallow neural network. But for the shallow neural network, the estimation error is better than the deep neural network. So based on this result in this kind of paper, we just consider about in which cases we should use deep neural network, in which cases we should use shallow neural network. The result is very simple. The result is that here we can first consider about one curve. Okay, only consider about one curve. If you just consider about one curve will just describe one kind of regularity of the loss function. And if the sampling point, can be a number of data point, the number of sampling points is located here and is very large, and the number of parameters is very small. If your neural network is satisfy this kind of cases, which means that okay, the number of points, the number of sampling point, and number of parameters will located in left of this kind of blue curve. In this kind of cases, which means that under this kind of situation, if you want to approximate some target function measured in the L2 loss function, you should use deep neural network, more deeper neural network. Otherwise, if the sampling point and number of parameters located at the right hand side of this blue curve, you should consider about wider neural network. And the more interesting things is that we find that when the regularity of loss function is increased, we find that deeper neural network will become the deep neural network range, which describe deep neural network is better range, which become larger and larger. So this gives us suggestions that if the regularity of your loss function is very large, maybe you should consider about the deeper neural network to solving this kind of problem, not the shallow neural network. Okay, and this paper shows this kind of results, but our paper is more about theoretical. So for the experiment, we just do the very two cases. Okay, so we just consider about target approximate target function in the L2 norm. So we can find that here we establish shallow neural network and a deep neural network. Deep is for shallow neural network, deep is 1 with is 20, and for the deep neural network, deep is 4 with is 10. So number of parameters will become exactly same. And we find that when data is very you have a lot of data, okay, deep is better. But if you just have very small data, okay, shallow is better. So this is some very very simple experiments, but it can already can support our final result. Okay, so this will become the generation error. So in the first part, I proved that the approximation error deep neural network is better. But if you want to see this better in the experiments, what you need to do is that you only can see this good performance when you have lot of sampling points and also your parameters not very large. Then you can see this advantage for the deep neural network. Otherwise, shallow neural network is still the good way to solving the problem, solving the PDE. And also, if the regularity of the loss function is very high, maybe you can consider about some loss function. Okay, so this is my today's talk. Thanks.
Thanks a lot. It's a very interesting talk.
Okay.
Um, does anyone have any questions in the audience?
Hmm.
Great. Oh yeah, Riam. I think you're on mute, Riam.
I cannot hear.
Yeah, Riam can hear you. Riam, do you have a question?
Uh, you are mute yourself.
Can you hear me now?
Yeah,
Yes.
yeah, yeah, yeah.
Okay. Sorry, microphone. Okay, so can you go back to page 10?
Page 10. Okay. Page 10 is is this one. Oh, this one. Okay. Okay.
Yeah, this okay, so the last one, condition 2, that is omega, the kth derivative of omega, right?
Yeah, yeah, that's right.
And you mentioned that omega can be taken to be 10h, but
Mm-hmm.
I'm I mean omega can be 10h, right?
You mean that you mean sigma can be 10. Yeah.
Yeah, okay, so I'm experimenting now on Desmos, but when I take higher derivatives, I see an explosion of derivatives around zero. So
Oh,
wouldn't
yeah.
that be a problem?
Yeah, that's a good point. Here, this condition we will not require the domain near the zero. We just require the behavior when case x is very large. Okay, you are right. When case when x is yeah when but I think that for tanh when x is near the zero, this inequality still hold, right? It's, it still hold because that this part will become very large.
Yeah.
At the tanh is always bounded. The derivative is always bounded. So
Yeah.
this is still hold. Yeah, still.
Maybe can I share my screen for a second to let you see?
Sure. Okay. Okay.
Uh,
Okay.
yep. Good.
Okay, can you see it now?
No. Oh no. Yeah, yeah.
Okay, so this is 10h,
Mm-hmm.
and when I take higher derivatives, you can
Mm-hmm.
see it's exploding, and
Yeah,
and
but
this
the
explosion is affecting
yeah,
more and more areas. So how is that gonna?
Yeah, but I
yeah,
guess
yeah,
if I
yeah,
can just say one thing, I guess the point is that you can always choose. It's large but still bounded, and so
yeah,
you can
but
always absorb a lot into that constant just by taking the soup over all first k derivatives on like the small
mm,
compact interval around the zero. But that's what you're gonna say,
yeah,
right? Huh? Yeah, yeah,
yeah, I agree with that.
yeah.
Yeah.
Because
Because that
also his upper bound is very large. It's one over
yeah, yeah,
x.
yeah, but that part will become infinite.
Exactly.
Yeah,
It makes
yeah,
sense. But it's a good
yeah,
Yeah,
question.
right.
yeah, yeah.
Okay. Okay. I have a second question. So can you go back to
Okay.
page 9
Uh,
where you had the
Page 9. Okay.
yeah
Sorry. Wait, page. Okay, this one. Sorry. Page 9. Okay. Piecewise linear
yeah
function.
this one. So can you explain in a little more detail how you avoid this small region, so this small so-called traveling area?
Because based on the partition of unit, I just first of all I establish a approximation near the on the whole domain, but except this small range, and then I establish the partition of unit by neural network and make that partition unit support set is this part this small range is outside of the support set for that partition of unit. and then I just need to combine all the partition unit together, and then in this part you can just totally remove this small range. Mhm.
Yeah, but I mean, if you're putting these regions outside the
Mm.
the support, but how would you still consider that region? I mean,
I will
I,
use a new neural network to approximate that region. So because here we have assumption, right? So this is a very good point. So here, this neural network can only approximate in a whole domain with some small range. And then I going to establish another neural network to approximate that small range. But that neural network will have another bad domain. So that bad domain, I will just use a partition unit to remove it, but use the first one to approximate it.
oh,
Yeah.
I see.
Yeah, yeah.
This approach in John's paper is like you're taking some kind of like median of
Y-
like three functions, right?
not like the median user. You can use a POU to totally achieve it at sum them together. It can achieve the approximation in the whole domain. You don't need to choose a median, something like that. Yeah. For each part, for each point in the domain, I can find there is a neural network to
Yeah.
achieve the approximation. Mm.
Maybe I ask one thing,
Okay.
because
Mm.
first thing I have to go.
Okay, yeah, me too.
But I would suggest, like, since the conversation seems nice, if you guys want to, like, don't be shy to send
Mm.
Yahong an email. Like, you guys have a lot in
Yeah,
common. It's
yeah.
approximation.
Mm.
Um, but honestly, really great talk, and
Mm.
hopefully, I'll see you around. Honestly, I'll keep reading the paper.
Okay,
Yeah,
okay,
thanks for
good.
having.
Thank you.
Thanks for joining.
Mm.
Yeah.